Hello, this is Math Jazz from Almost Cool. I am here giving a calculus live stream. I'm sorry I am late. I had to do some fixing of my software because I just got a new computer and it took me longer than I expected to be able to fix and tweak all of the settings to get this to work. Anyway, um, if you have any questions, you can you can say them in chat, or if you need to write special math symbols, you can write on a piece of paper and email your questions to mathjazz9@gmail.com. I will put that in the chat right now. So, here we go. mathjazz9@gmail.com. Anyway, I have a list of questions to solve for you guys, and I will be doing those if I have no questions from you. When I get to the end of them, I will stop, and then I'll be done. So, first question. You see, I thought that I'd focus on writing questions about work, about force and distance and work, because I think that those are confusing to a lot of people. Anyway, the first question, lifting a rock. This is actually, there's no calculus required on this question, but I think it's a good starting point. Suppose that a 1,000 kilogram rock is lifted 5 meters. How much work is done in the process? So, well, this is not so bad. The force on the rock is the mass times gravity. Mass is not a force. If we're doing a problem in the standard system or the imperial system or the US system or whatever you want to call it, then you're given a force of an object, not the mass of the object. We measure things in pounds. The equivalent unit for measuring mass is the slug in the imperial system. But since we were working in metric, we first have to convert our mass into a force before we can do anything about this problem. Now we have a constant mass 100 kilogram rock, which means that we'll have a constant 9,800 Newton rock that's being lifted. That's its weight. The weight is a force. And so first we have to multiply by 9.8. We have here 9.8 meters per second squared times 100 kilograms. That's the force. To get the work, we multiply force by distance, so we multiply that by 5 meters, and we end up with 4,900 kilogram meters squared per second squared, which I believe is, I believe that's in joules. I think work is measured in joules. But the problem will come with our calculus when we have either forces that change or we'll have distances that change. That sounds really odd. A rock either moves 5 meters or it doesn't. But the problem that we have is with our rock, we can consider it a point mass, and we can move it around like a solid, rigid object. But when we're pumping water, that's not a rigid object, and the water that's at the bottom of our tank or further along the pipe has to travel a different distance than the water at the top of a tank or closer along a pipe. So the two ways that we need to use calculus, or the two types of problems that we need to use calculus on, are either where we have an object that is gaining or losing mass as it's moving, but we can basically consider the object as being a solid object that moves a set distance. Or we can have an object that isn't really gaining or losing mass, but its mass is spread out, and the different parts of the object move in different ways. So, first few of these are going to be examples of a an object that is either picking up or losing mass as it's traveling, and we have to figure out what the work is being done on that object. So, um, so we have a spring. This is actually not a change in mass, but it is a change in force. It's the same type of problem. It falls into that first category of we have an object that is traveling some distance, and the force is somehow changing, either because it's gaining or losing mass. In this case, it's because the spring it exerts different amounts of force when you put different amounts of compression on it when you compress at different distances. So suppose that the natural length of a spring is 5 meters. This is a huge, huge spring, but it's the one that we're going to work with because converting between centimeters and meters is not calculus, and it is kind of tedious. So we have a long spring. It's 5 meters long. And it takes 60 newtons of force to compress the spring to 1 meter. So this spring is very loose. It is, this is not, this is a very, well, the opposite of what this spring is a stiff spring. This is a spring where barely any weight causes it to compress quite a bit. The question is, how much work is done during this compression? So, first, we remember that the force required to compress a spring is a linear function of the amount the spring was compressed. So the force is always going to be some constant k times the distance of compression x. And this k is called the spring constant, surprisingly enough. Anyway, the spring constant times the distance compressed is the force, but this force changes at every distance. So we can't say that it was a set force of kx times a distance of x. Kx being the force and x being the distance that was traveled. So kx times x is what someone might naively think the work done is. But since the force is changing, and we all know this, when we are stretching a spring, it gets harder to stretch the more we've stretched it. Anyway, we have to do calculus, and that means that we have to do an integral. It's going to be, force is going to be a function of the distance that we've already compressed, and we're going to multiply that by a differential distance dx. So we can't do f times d, we do f of x, this is the force at distance x. We multiply it by a differential distance dx, and we integrate that over the entire length of compression. So now that we know where we're going, which is we're going to try and find a force function, and we're going to integrate it with respect to distance. To get that force function, we need to know what the spring constant is. So we need to figure out what k is. Fortunately, we know that 60 newtons is the amount of force required to compress the spring from 5 meters to 1 meter. So that means that 60 is equal to 4, which is the amount of compression. It went from 5 to 1. That's 4 meters of compression, times k. So solving for k, we get k is 15. Now, like we discussed before, we have to integrate from 0 to 4. That is, it started off with no compression, and it's going all the way up to 4 meters of compression. We're integrating 15x is our force function, and dx is our differential distance. And that's not a hard integral. We use the power rule to get an antiderivative. We plug in our values. This was a different problem that didn't get deleted. So we plug in our 4, we plug in our 0, we get 15 over 2 times 16, and that's going to end up with 120, that'll be 120 kilogram meters squared per second squared, or I believe that is joules. Okay, so now for part B. How much work is required to compress the spring to 3.5 meters from its natural length? So, if it starts at 5 and it compresses to 3.5, that's a compression of 1.5 meters. And we use the same force function, and we use the same differential distance, so we get the integral from 0 to 1.5 of 15x with respect to x. We use our power rule to find an antiderivative. We plug in our endpoints. We note that 0 will kill off the antiderivative. And we end up with 135 over, that should be over 8. That's a typo. 135 over 8. Okay. So, problem 3 is another spring problem. Suppose that the natural length of some spring is 10 centimeters. We're going to compare. I think that I may have done this problem for 10 meters instead of 10 centimeters. Compare the work required to stretch the spring from 10 centimeters to 20 centimeters to the work required to stretch the spring from 20 centimeters to 30 centimeters. Yes, so these integrals will come out with numbers that will be, since we didn't convert from centimeters to meters, these are actually going to be in kilogram centimeters squared per second squared, which is a strange unit. I think that is 1/10,000th of a joule. It's a pretty small unit. But so long as we know that these are not in joules, they are in 10,000ths of a joule, then the numbers are fine. The math is correct. So we set these integrals up just as we did before. We have the integral from 0 to 10 of kx with respect to x, and work 2 is going to be the integral from 10 to 20 of kx dx. And we get these antiderivatives. We plug in the appropriate values for the endpoints of the interval. And we end up with 50k and 150k, which are probably actually 0.005k and 0.015k if you wanted to convert into joules, but we don't need to. And what this says is that it takes more work to stretch the spring from 20 centimeters to 30 centimeters than it does to stretch the same spring from 10 centimeters to 20 centimeters, if 10 is the natural length of the spring. And this is independent of K. So, however stiff your spring is, you're still going to get the fact that it's easier to stretch or compress the first 10 centimeters, then to stretch or compress the next 10 centimeters. Okay, so here is a lifting a leaky bucket problem. This is actually very similar to the spring in that you're going to have to integrate a force function, that is, a function that gives you force when you give it distance, with respect to a differential distance. This is different from um, all of our pool problems where we're emptying a pool and having to pump out the water, because those problems are of the second type that we talked about earlier. Those are problems where if you are your object that you're moving is not rigid, and parts of the object move a lot and other parts of the object don't move very much. This problem, the whole object moves as a single rigid bucket full of water. And so we use that first type. We find a force function and we integrate it with respect to distance. So here we have a bucket that weighs 10 pounds and initially contains 30 pounds of water. Suppose that every foot the bucket loses 2 pounds of water. How much work is done lifting the bucket 5 feet? So we're going to consider this as a rigid point mass traveling a fixed distance. And the calculus is going to be because the force is changing at every distance. So we need to find our force equation. We started with 10 pounds of bucket and 30 pounds of water for a total of 40 pounds. At every foot, we lost 2 pounds of water. So at a height of x, the bucket will have lost 2x pounds of water. So the force at a height of x is given by f of x equals 40 minus 2x. Notice we don't have to multiply by gravity because we were in the standard system, and the standard system gives you weights, not masses. So we don't have to do any multiplying by 9.8. Okay, so now we just have to integrate this force function with respect to x. Our endpoints are 0 and 5 because the bucket travels from height 0 to height 5. And the integrand is 40 minus 2x. We find an antiderivative. We plug in our endpoints. And then we simplify. So this takes 175 foot-pounds of work to be able to lift this bucket 5 feet. Problem 5 is another leaky bucket problem. Suppose that a bucket weighs 10 pounds and initially contains 30 pounds of water. Suppose that every foot the bucket is lifted corresponds to a loss of 2 pounds of water from the bucket, and that the 8 feet of rope on which the bucket hangs is 1/2 pound per foot. How much work is done lifting the bucket 8 feet? So this one's pretty similar to the previous one. I used the same numbers for most of the problem. However, now we're not only losing weight of water through leaking, we're also losing weight of rope through having the rope rolled up on a spool. So, we still have to do the same type of problem though. We find a force equation. We have 10 pounds of bucket, 30 pounds of water, 4 pounds of rope for a total of 44 pounds. At a height of x, we will lose 2x pounds of water, and we will have lost half of x pounds of rope. So our force equation is going to be the force at height x is equal to 44 minus 5/2 x. That is another typo. I'm sorry. 44 pounds for the bucket, water, and the rope. So we integrate from 0 to 8 of 44 minus 5/2 x to get the work. The integral from 0 to 8 of 44 minus 5/2 x is equal to 44x minus 5/4 x squared from 0 to 8, which is equal to 44 times 8 is going to be 352 minus 5 times 64 over 4 is going to be 80. So 352 minus 80 is going to be 272. 272 foot-pounds of work. Okay, so now we have a solid of rotation, okay? We will probably end up doing a pumping water out of swimming pool problem at the end. Again, if any of you have any questions you'd like me to focus on, please send your questions to the email that's in the chat, or if you can type it into the chat, that's fine as well. Now, this solid of rotation, we're going to take the same region and we're going to rotate it once around the x-axis and once around the y-axis and see each of the volumes generated in this way. It turns out that they are different. The direction that you are rotating actually does matter in determining how much volume the solid has. The first problem is we're going to obtain the volume, or we're going to find the volume obtained by rotating this region about the x-axis. When we look at this type of a problem, it's useful to draw a picture. So I'm going to pull up Desmos. So we have one of our functions is x squared, and the other function is x cubed. Now we're only caring about the region between 0 and 1. So here we go. The region between 0 and 1. And we want to rotate around the x-axis. So that's going to be around this direction. I don't know if you can see my mouse. Oh, there it is. Okay, so looking at this region here, we notice that it's easiest to integrate in the x direction. dx is the direction we want to integrate because the difference between these two curves is very nicely a function of x. If we wanted to write them as a function of y, we could, but that would mean going from a polynomial to a difference of radicals. And so it's nice leaving them as functions of x. So if we want to find the region rotated around the x-axis, we're going to have the integral. We're going to have an integral that the rectangles are going to be formed vertically, and they're going to be rotated around a horizontal axis. So that means that our rectangles are perpendicular to our rotational axis. So we're going to use the disk method. Okay, so we're going to use the disk method. The disk method says that we're going to have to break this into two integrals, an outside rectangle to represent the solid object, and an inside rectangle to represent the portion from the inside of this object that is being removed. So the outside rectangle is going to be x squared tall and dx wide. The inside rectangle is x cubed tall and dx wide, because of, if we remember, x cubed was the smaller function on the interval. We take the square of the height of the rectangle, and we subtract the square of the height of the inside rectangle. We integrate with respect to x over the interval 0 to 1, and we multiply what we get by pi. Here's our integral. Pi times the integral from 0 to 1 of x to the fourth minus x to the sixth dx, because we square the x squared, which is our outside region, and we square the x cubed, which is our inside region. So from here, we find an antiderivative using the power rule, and then we plug in our endpoints, and this should be a fraction 1 over 7. And when we subtract to simplify, we have 7/35 minus 5/35, leaving 2/35, and multiplied by pi, we get 2 pi 35. That is the volume obtained rotating the region about the x-axis. Now, if we want to rotate this region around the y-axis, we can't use the disk method because the y-axis is vertical, and the rectangles that we decided to use are also vertical. So we have to use the shell method. So if we're going to use the shell method, the distance between a rectangle and the axis is x. The height of the rectangle is going to be x squared minus x cubed, because x squared is the taller, the higher, the bigger function on the interval. So we take the bigger function minus the smaller function to get a positive number. So what we're going to get as our integrand is x, which is the distance away from the rotational axis, times x squared minus x cubed, which is the height of a differential rectangle. And we have to multiply the whole integral by 2 pi, representing, of course, if we take the 2 pi and the x, which represents the distance from the rotational axis to a rectangle, 2 pi x would represent the distance around, along the rectangle as it's, along the wall that the rectangle generates as it's being rotated. So we get an integral that looks like this: 2 pi times the integral from 0 to 1, which is our region that we're integrating over, times x, which represents the distance from the axis, times the quantity x squared minus x cubed, which is the height of a rectangle, times dx, which represents the width of that rectangle. So this integral gives us the volume of the solid of rotation. We perform multiplication to simplify the integrand. We find an antiderivative using the power rule on each of the terms. We plug in the endpoints and take the difference of the antiderivative at each of these points. We note that 0 kills the integrand, so we don't need to plug that in. And then we simplify. 1/4 minus 1/5 is equal to 5/20 minus 4/20, which gives us 1/20. Multiplied by 2 pi, we get a 2 to cancel in the numerator and denominator, leaving pi over 10. We notice that pi over 10 is not the same as 2 pi over 35. And so the same region rotated in two different directions gives us two different volumes, even though it was the same distance from each of the axes. I mean, x squared and x cubed both hit the origin, and so they both touch both axes. But it's remarkable that we get different numbers just by changing the angle of the rotation. Okay, so next question. Oh, we ran out of the questions from this set. Do we have questions in the chat? I don't see any. So I'll just pull up a past semester exam. We can work on those. So let us look at a problem. Here's a nice problem. So I'm going to, let's see. I am going to go to tech. There we go. So let us find it. Here is our problem. There we go. I'll just pull this over here. Okay, so we want to evaluate this integral, but we don't know what the antiderivative of x squared square root of 4 minus x squared is. But we do notice that there is a square root, and inside of it is a number minus the square of a variable. So we feel like what we should do is a trig substitution. Okay, so let us try that. The substitution that I want to try is 2x equals, let's see, we're subtracting, I'm thinking that this wants to be sine of theta. So let us try that. 2x equals sine theta is going to be our attempt at a trig substitution. So that would mean that 2 dx is equal to cosine of theta d theta. And if we do this, then we can substitute this back into our integral, like so. So our dx becomes cosine theta d theta. We have a half that we have to add to this, that the denominator. the x squared is going to become, looks like sine squared theta over 4. And I'll pull the 4 into the numerator. And 4 minus sine squared, well, 4 minus 4 sine squared, we're going to get square root of cosine squared. 4 will come out as a 2. And let's check to see if I did that right. Got there we go. Parentheses are important. Let's see, so did we substitute that correctly? We have x squared is going to be sine squared theta over 4. Here's the 4, here's the sine squared theta. We have dx is equal to cosine of theta dx over 2. It's cosine theta dx over 2. The 4, it's factored out of the square root as a 2. We have 1 minus, once we factor out the 4, we have 1 minus sine squared theta, which is cosine squared theta. Let's put our theta in here. And that looks great. Looks like this 4 cancels with both of those 2's, so let's write that in there. So this 2 goes away. This 2 goes away. And the square root of cosine squared is just cosine, so the square root goes away too. And now we have, oh, here it is. Yes, this is what we had. This is what we have after canceling. That 4 goes away. There we go. Oh, and the cosines cancel, which is really nice. So let's write that in as well. Cosine theta cancels with cosine theta. So what that means is we just have the integral of 1 over sine of sine squared theta. We notice that sine squared theta is cosecant squared, so we can get rid of this fraction because fractions are kind of annoying. So we get cosecant of theta, and it's squared. And we know that the antiderivative of cosine squared theta is going to be negative cotangent of theta, plus a constant. Here we go. So we use this trig substitution. We get this when we've substituted. We clean it up a bit, canceling constants out, canceling spare terms out, rewriting 1 over sine squared as cosecant squared, and then remembering that cosecant squared is the derivative of negative cotangent. And here's our constant of integration. So that's pretty easy. I mean, there could be much worse trig substitutions out there, but this one was pretty nice. Okay, so let's look at the next question. Next question is, what is the average value? What is the average value of h of x when h of x is equal to 5 pi cosine to the fourth x sine x on the interval 0 to pi? So this here looks like it's just a u substitution. So let's try that. Let's see. Let's try u equals cosine of x. That'll give us as our du will equal negative sine of x dx. Okay. So we rewrite this integral as our interval is pi long, from 0 to pi of, looks like 5 pi u to the fourth du, and we need a negative sign on it. Put the negative sign on this fraction here. It doesn't like when I... Anyway, so sine x dx became negative du. Here's the negative sign. Here's the du. Cosine to the fourth x became u to the fourth. The 5 pi is a constant, so we leave it alone. And pi was the length of the interval, so we divide by it. This integral will represent the average value of this function. Oh, but since we did a u substitution, x went from 0 to pi. U goes from cosine of 0 to cosine of pi. So let's switch those endpoints up to. Cosine of 0 is 1. Cosine of pi is negative 1. Okay, so this is the correct integral. Since the top limit is negative and the bottom one is positive, I'm going to switch the signs to be able to I like having the top limit being bigger than the bottom one, so I'm going to switch that by flipping the sign of the integral. This negative sign went away so that we could switch the negative 1 and the 1. Oh, we have questions. Are these questions representative of the ones on our exam? Yes, this exam was an exam from a previous semester. They pretty much look like this because we pretty much write our exams by looking at old exams and changing numbers. As in fairly easy numbers on the volume equations. We try to make them nice on the volume equations. We do. That said, sometimes you're going to get square roots or something. And if you get something like that, then you just leave it as a square root. You try not to make it... we don't expect you to approximate square roots or anything. In fact, if you approximate any of these roots, if you try and give 5 decimal places of some, pi times 3 times the square root of 2 or something, it's going to annoy the grader. It's not going to be impressive to the grader. Well, I mean, when they plug it into the calculator, if you did it right, it'll be impressive, but they'll still be annoyed. So just leave expressions as they are, and usually the numbers will work out. Okay, so yes, let's oh, So from here, what we need to do is we need to find the antiderivative using the power rule. So let's do that. So we're going to get by the way, what I'm using right now to write this is called LaTeX. And if you're planning on a career in the sciences, you will probably need to learn. That went from -1 to 1. There we go. So, and the power goes up by 1, and we divide by our new power, and hey look, the pi's cancel out too. That's pretty nice. So we get 1 to the 5th minus, so we get 2. Looks like the average value of this function on the interval provided is 2. See, the numbers do come out nicely on exams a lot of the time. I mean, this was definitely chosen so that it would end up as 2. So let's look at the next problem. Actually, I tried this one earlier, and it is hard, and it is harder than anything on the exam that you're taking. So we're going to skip number 4. So number 5, evaluate this integral. Okay. Actually, I think that we should do a water pumping problem. This is a bucket. That's not a... That's finding the volume of a rotation. I really want to do where you have a pool or a vat or something and you're pumping all the liquid out. Let's look for one of those. Let's see. There you go. Okay, so not that one, not that one. This is another rope and bucket one. Well, uh, okay. So let's suppose that we have a cone. Let's draw a nice cone. Here's a cone. Can you see this cone nicely, all of you? Guess I didn't make that one long enough. Go. There we go. Here's a cone. I can draw a cone. So we have this cone here, and let's say that it is let's say that this cone is 15 feet tall and 5 foot with a 5-foot radius. So 15 from here to here. And a 5-foot radius. There we go. Beautiful. So we want to pump all of the water out of this cone from the bottom of the cone to the top. Did I say feet or did I say meters? That doesn't matter. Whatever it was, it's in feet now. Okay. So we have um that's not really integral shaped. There. That's our integral sign. So we're going to have to integrate from 0 to 15. We're going to have to integrate. Oh, okay. So I guess I skipped ahead a little bit. First, we want to talk about to find the work that's involved in doing this. We're going to have to figure out a distance and a force. Distance times force is work. The problem is that the water at the top of the cone doesn't have to travel far to get out, and the water at the bottom of the cone has to travel really far to get out. So we need to find chunks of water that all have the same distance to travel, and we're going to multiply those chunks by how heavy they are. So if I take this cylinder here, I know it's so bad, but imagine that is a coin shape cut out of the cone. So this cylinder here, we notice that it is going to be dx tall, but to get the volume of this piece of the cone, we're also going to have to figure out the area of the circle on top. So that means we have to find the radius. Radius squared times pi gives us the surface area of the top part of the cylinder. It'll give us the area of the base, the area of the circle. And then multiplying by dx will give us the volume of that part. Ah, we have a problem. Yes, I can do number 12 on the practice exam. I will need the practice exam emailed to me because Dr. Fisher didn't send that to me, I don't think. But yeah, if you could take a picture of it and send it, then I'll put problem 12 on the video. Okay, so getting back to this, we want to find the volume of the cylinder here. The height is dx, and we need the radius. So we need a relationship between how tall we are, or how far up we are the cone, and how big the radius is. Fortunately for cones, well, cones are just triangles that are rotated. And triangles have this really nice property where whatever the ratio is between the height and the base, That's the same ratio regardless of where you're looking. So at this height, it's the same ratio from here to here as it is from here to here. And at this height, it's the same ratio from here to here as it is from here to here, and so on. So since this is 15 to 5, that is, the radius is a third of the height, that's the same ratio everywhere. If we were a height x, the radius is a third of x. So our integral, we put 1/3 x as our radius, which means 1/9 x squared will be pi times 1/9 x squared is the surface is the area of the circle here. So let's write that down. Let's see. Do they have a pi? I think they do. Okay, we're gonna write pi like that. Pi times x squared over 9. Here we go. So here we go. So pi x squared over 9, not times 9. There we go. This is a really nice integral here, but it is not the work integral. What we've done so far is each of these differential slices, that is this chunk here, is the volume of a cylinder, and the sum will add up all of the cylinders from the bottom to the top. This gives us the volume of this cone. We don't want the volume of the cone, we want the work. But the volume of the cone is a good first step. So, what we need to do now is we need to convert from a volume of a cone to a weight of water. Fortunately, that's not hard. We know that if this is how many cubic feet of water there is, we know that every cubic foot of water weighs 62.5 pounds. So if we multiply by... That's weird. If we multiply by 62.5 pounds, then we're going to convert from a volume of water to a weight of water. So this integral here gives us the weight of the cone of water. But that's not what we want either. What we want is we want to know the work that's done. But this function here, this gives us force. Now if we have distance, we're done. So this chunk of water, this coin that we took out, this infinitely thin or infinitely short cylinder, is traveling from this location here to the top of the cylinder. And since we know that this is x away from the bottom, we know that the distance from the top is 15 minus x. So all we have to do is multiply what we have by 15 minus x, and that will give us the weight times the distance, which will give us Exactly what we were looking for, the work. Come on. Might have to just cut off that 15. There we go. There we go. And we'll put it back. So this is the integral that we need to solve. And guess what? Once we once we multiply through, it is just a power rule. There's an x squared term and an x cubed term, and we use the power rule and we're done. Okay. So this is not too bad. And this is how all of these these pumping waters out of cones or pools or whatever problems go. Is you find a differential cylinder. Sometimes it's not a cylinder, sometimes it's a differential rectangular prism, but you find it and then you integrate from the bottom to the top, or from the top to the bottom. We could have put 0 up at the top and it would have worked just the same way. Gotten the same numbers. Anyway, I wanted to do one of these. 62.5 is the weight of a cubic foot of water. And it is something that we expect you guys to know. Although, I bet it does show up on exams. I think that they might give it to you half the time. But the other half the time they won't. And 62.5 is just going to be something you're just going to have to know. The other thing you'll have to know is that the acceleration due to gravity is 9.8, and that water has there are 1,000 kilograms of water per cubic meter. So if you're working in metric, you're going to need to multiply by both. We multiplied by 62.5 to convert from a volume of water to a weight of water. You're going to have to multiply by, if you're working in metric, you're going to have to multiply by 1,000 instead of 62.5 to convert from a volume of water to a mass. And then you're going to have to multiply also by 9.8 to convert from a mass to a weight. I'm going to try finding problem 12 on the practice exam. Let's see. Oh! Oh, that didn't give it to me. Okay. Yeah, it looks like Dr. Fisher didn't email me the question. Does anyone on chat have, will we have to memorize 1,000 and 9? Yes, you will have to memorize the 1,000 and the 9.8. Does anyone in the chat know what problem 12 is on the practice exam? So I think that there might be lag between oh. Until then, let's do another problem. Okay. So oh yeah, this was one of the ones we were looking at. The natural log. Okay, so this is going to be a U substitution of some sort. Let's see. Problem 8. That's yeah. Okay. So we want to do this integral. So let's see. What do we want U to equal? Well, U's got to equal either let's make it equal the square root of y. U equals square root of y. Okay, so that would mean that du is equal to, let's see. It's going to be 1/2 times the square root, sorry, times y raised to the negative 1/2. That sounds right. Oh, times dy. Okay, so it's going to be this, and it's going to equal this. Here we go. And so the 1 over square root of y dy is this part. We have to get a half in there, so let's make our integral is equal to du. The denominator becomes nothing. We take it out. Two here. When we plugged in 4 to y, we'll get out 2 for u. We'll get out 3 when we plug in 9. ln of y becomes, well, if square root of y equals u, then y is equal to u squared. So we'll get ln of u squared du. I think there's a 2. Yeah, there's the 2. So here we go. So this integral, when we do our substitution, 4 for y becomes 2 for u. 9 for y becomes 3 for u. ln of y becomes ln of u squared. And since du is 1/2 of y to the negative 1/2 dy, here's the y to the negative 1/2, here's dy, we needed a half, so a 2 is left behind to balance. Oh, 12 is a bucket problem that we went over already. Okay. Yeah, bucket problems are important to you guys. Just in case you wanted to know. I don't know if it's a leak or a rope that's being wound up, but they're important for this exam. Okay, so we have this integral now. We use the property that log of a base to a power is going to be the power times the log of the base. So this integral here becomes this power of 2 on the u. It's pulled out in front, multiplied by the 2 that's already there. Like so. 4 times the natural log of u with respect to u. There is an antiderivative. I think it's natural log of... Wait, let's see. I think it's u minus u times the natural log of u. I think that's the antiderivative. Let's check. I'm going to do some scratch work here. If we have u minus u ln of u, and we take its derivative, what happens? We get one minus ln of u minus 1. And that's the incorrect sign, so let's switch that. U ln of u minus u. That'll flip these signs. That looks correct. Okay, so the antiderivative is going to be u ln of u minus u. The whole thing gets multiplied by 4 because that was the constant we had. And our limits were 2 and 3. Two and 3. Okay, so when we plug in 3, we get 3 times the natural log of 3 minus 3. When we plug in 2, we get 2 times the natural log of 2 minus 2. And we subtract those. But from here, it's no longer calculus. It's just plugging in numbers and subtracting and stuff. So we can let that be done where it is. Let's see. This one is easier than it looks. Okay, so we want to evaluate this integral. But the first thing that we notice is that tangent is just, well, it's sine over cosine. So we have 6 cosines in the numerator, and we have 3 in the denominator. So let's simplify this already. Okay, so this is a simplified form. Cosine cubed x, sine cubed x. And from here, we want to convert 2 of these sines into cosine using our Pythagorean identity. So we do that. Sine squared is equal to 1 minus cosine squared of x. And we're left with 1 sine. Okay, so this is what we get. When we multiply that out, we're going to have see. Well, we get cosine cubed minus cosine to the 5th, everything times sine. I like having the parentheses around. Oh, and from here it's just u substitution. We let u equal cosine. So that's not too bad either. I mean, you just let u equal cosine, then you get u cubed du. That's not bad. I will put my parentheses here, because we need them here and here. Okay, so we'll skip that because we know how to do u substitutions. Find the volume of a pyramid whose base is square, with side length of the square 3 meters and height 4 meters. Okay, so this is something that you should know how to do. So what we need to do is we need to find. Let's draw a picture. We're gonna draw a picture. There we go. So we have this pyramid, and it looks something like this. Except that it is pretty instead of like that. Okay, so we're told that the pyramid is 4 units tall. We're told that the base is 3 units wide. Side length of the square is 3 meters. Okay, so this distance here is 3 meters. Okay, so from here, we're going to integrate from the bottom to the top. Well, from the top to the bottom. Let's say that the top is height 0, the bottom is depth 4. And we're going to take out little chunks like this. Here is a chunk. They're going to be dx tall. And just like the cylinder, the differential cylinders we used for the water problem, we're pumping water out of a cone. The volume of one of these differential rectangular prisms is going to be the height, which is dx, times the area of the face, which is the area of a square. Now, we have a triangle relation here. We have a relationship of 4 to 3 between the height and the base. So that means that the height and the base of this chunk that we just selected, this rectangular prism, this square coin that we cut out of it, if it's going to be x away from the top, then it's going to be 3/4 of x in the base. This chunk is 3/4 of the way down, but for every 4 units of length we go down, we have a base that is 3 units of length wide. We have 1x down means we have 3/4 of x wide. So that's going to give us the area of our square. We're going to have 3x over 4 is going to be the length of one of these sides here of this square coin. And then the square of the length is going to give us the area of a face of the coin, and then times dx is going to give us the volume of this little region here. So, and I need a 2, but I need it smaller. There we go. So let's assemble this. 3x over 4 squared, and I need a parenthesis there, I guess. So our fraction bar, there we go. And parentheses. Go. This goes up here. They're tiny little parentheses. Okay, so we have this represents the volume of one of these square coins. And then if we take all of, maybe I can do this. There we go. Almost. The integral from 0, which is this point here, down to 4, which is the base, is going to be the volume of this pyramid. 0 to 4. And from here, this is just a power rule, so we won't bother solving the integral. But this is how you set it up. That's really the hard part, is setting it up. Okay, are there any more questions in chat? I mean, I don't see any questions in chat, but for those of you who are still watching, are there any topics that you feel like you want to go over? I think we've covered one problem of every type so far. Okay, so if there are no more questions from chat, I think that I've covered everything that's going to show up. Every type of problem that's going to show up. So I mean, this is a cool graph. Zoom in on it a little bit. Still no questions? Okay, since there are no questions, I just want to tell you all thanks for watching, and I will see you in class tomorrow. If you have any other questions about anything in the class, send me an email, and I will make a video on the topic. So, have a great day, good luck on your exam, and goodbye.